Okay, welcome back to chapter 1, to the last section that we're going to cover in this chapter, which is inverse functions. Super exciting. So in this section, we're going to talk about what inverse functions are and how to see if two functions are inverse functions of each other. We're going to use graph of functions to determine whether they even have inverse functions. We're going to use the horizontal line test to determine if functions are one-to-one. And then we're going to find inverse functions algebraically. Okay, so we know that a set of ordered pairs can represent a function. For example, the function f of x is equal to x plus 4 takes its inputs x and adds 4 to it, and it spits that out. So let's say you have, so f of x takes the elements in the set A, 1, 2, 3, 4 to the set B. So 1 plus 4 would be 5, 2 plus 4 would be 6, 3 plus 4 is 7, and 4 plus 4 is 8. And then the function can be written as follows. So here the function consists of these points, 1, 5, 2, 6, 3, 7, and 4, 8. Now the inverse function, so remember when a long time ago now it feels like, we talked about a function as a path or a mapping that takes one set to the other. The inverse function would take the output back to the input. It's kind of like it goes in the reverse direction, okay? So if you change the first and second coordinates, you would form the inverse function of f, which is denoted by f inverse. We read this little one as f inverse. Okay, now this is different than the exponent, right? Like the 1 over x situation. This is particular to a function, and we say this f inverse. Okay, so function from the f inverse would take set B to the set A, and it would be written where we basically switch x's and y's. So it would be x minus 4, where we have 5 takes us to 1, 6, f inverse takes us back to 2, 7, f inverse, 7 minus 4 would be 3, 8 minus 4 would be 4, okay? So here's a good picture, okay? So let's say you have, so notice here, so you have the domain of f, which is x, all the x values. They take, the function f takes these x values and gives an output, and all that output is the range, okay? But now the f inverse goes from the range to the domain. So in this case, the range of f is considered the domain of f inverse, okay? So this is like basically the outputs become the inputs, and then the inputs become the outputs. So this would be the range of f inverse. So the domain of f is the range of f inverse. Okay, so I'll just let you process that. You can think about it for a second. So in other words, if we were to do the composition of f with f inverse, or the composition of f inverse with f, we would find the identity function, because we would start with x, take it to f inverse of x, then come back using f, and then we would get x. We would get back to x again, okay? Or you would take f of x, right, then take f inverse, right, to go back, and we would get x again. Okay, so this is actually one way to tell if two functions are inverses, is to take the compositions and see if it equals to x. So what about informally? So what's a way to think about this informally? So let's find the inverse of f of x is equal to 4x. And then let's verify that the f of f inverse and f inverse of f are equal to the identity. Okay, so what does the function f tell us to do? The function f tells us to multiply each input by 4. Okay, so if the function f is telling us to do multiplication, what do you think would be the opposite or the inverse operation to get us back, right? So to quote unquote undo this function, we would have to divide each input by 4, yeah? So the inverse function of f of x would be f inverse of x is equal to x over 4. Okay, so it's like the inverse of this. This is multiplication, and this will be division. Okay, so let's verify that they equal to the identity. So f of f inverse means f of the inner function is f inverse of x, so f of x over 4. And then f tells us 4 times the whatever the input is. So 4 times x over 4 gives us back x. And then reverse f inverse of f of x is f inverse of 4x, and then 4x over 4 gives you back f again, x again. So now you've verified it algebraically. So yeah, so the definition of an inverse function includes this. We'd say that let f of g be two functions such that f of g of x is equal to x and g of f of x is equal to x for every x in the domain of g and every x in the domain of f respectively. So under these conditions, we can call g the inverse function of the function f. Okay, so we would say g is equal to f inverse. Okay, so we'd say f of f inverse of x is equal to x, the identity, and the f inverse of f of x is equal to x. So it's just a composition of functions, okay? So the domain of f must be equal to the range of the inverse, and the range of f must be equal to the domain of the inverse. So exactly. So in this case, don't be confused by that -1. It just means it. So when you have it right here with the f, it's always referring to the inverse function, and it's not referring to the reciprocal of f of x. Okay? I mean, unless the reciprocal just happens to be the actual inverse. Okay? So if the function g is the inverse function of the function f, it must also be true that f is the inverse function of the function g. So that's why we can say the functions f of g are inverse functions of each other. Okay, so what's up with the graph of an inverse function? Let's talk about that. Okay, so the graph of an inverse function. So let's see here. We have this graph of f. It's kind of like a weird thing right here. Okay, and its inverse goes here. And they're related to each other in the following way. So if you have this point AB on the graph of f, then, of course, since the domain becomes a range and the range becomes a domain, the point BA must lie on the graph of f inverse. Okay, so like if this was 2, 3, then this would be 3, 2, and it would exist, and it would be a part of the inverse of x, f inverse of x, right? Okay, so in other words, what does that mean? That the graph of f inverse is actually a reflection of f along the line y equal x, okay, because of this. All right, so it's basically reflected across the identity function, or y equals x. So you can see that here. So let's try to sketch these graphs on the same system to show that the graphs are reflections of each other on the line y equal x. So here we go. So we have f of x is 2x minus 3. That's a line. This is also a line, different line, but yeah. Okay, so here's 2x minus 3. There's a lot going on. So let's say this is y-intercept -3 and then a slope of 2, right? So this is it right here, a little steep. Now the inverse has a y-intercept of actually 3/2, so 1.5, and it has a slope of half, so it's a little less here. And if you notice, if you plot them, you'll have here, they reflect across the line y equal x. Okay? And you can test a couple points. So one -1, 1 exists, and one -1 exists, and so forth. You can see how they're inverses of each other. Right. So if you have this list, yeah, here's the same. Here's all those points. So -5, -1 exists on f, and then the reverse. So -5, -1 exists on f inverse. So if you have 0, -3 existing on f, -3, 0 will exist on its inverse, and so on. So you guys can see here where the domain and the range switch places. Basically, the domain becomes a range, and the range of f becomes the domain of f inverse. Okay, so now let's talk about one-to-one functions. Okay, so the reflective property of the graph of inverse functions kind of shows us how to, it's a nice way to see graphically whether a function is an inverse function, right? There is a test, okay? There's a horizontal line test for inverse functions, okay? So that's kind of cool. So you can say a function has an inverse function if and only if no horizontal line intersects the graph of f at more than one point. So if no horizontal line intersects the graph of f at more than one point, then that means that no y value is matched with more than one x value. So every output has a unique input, and since it's a function, every input has a unique output. So this is what we call one-to-one function. Okay, this is a function's one-to-one when each value of the dependent variable corresponds to exactly one value of the independent variable. And so a function f has an inverse function if and only if it's considered one-to-one. So let's look at this. F of x is equal to x squared, right? So here we have a table of values for x squared is f of x equals x squared. So -2 to 3. And we just square each one. So -2 squared is 4, -1 is squared is 1, 0 is 0, 1 is 1, 2 is 4, and 3 is 9. Okay, now this one is we switch the values. We switch the domain and range. So here's the 4 to -2 and then 4, 2, right? So you have two different values for y when there exists x. So that means that the table on the right does not represent a function because the input has two different outputs, okay? So f of x is equal to x squared is not one-to-one and does not have an inverse function. Well, I mean, okay, the only exception to this would be if you restrict the domain of x squared. In that case, yes, it would have an inverse, but we'll talk probably a little bit more about that. Okay, so how do we apply the horizontal line test? Well, you take the graph and you pretty much just draw a horizontal line, and if it only intersects once, then it's one-to-one and the inverse function exists. So here's the x squared minus 1, here's parabola. Okay, so this is not a one-to-one function and does not have an inverse. Okay. All right, so let's find these algebraically. So this is fun, I really like this. So if we have simple functions, you can see them by looking, right? You can tell out what the inverse is by looking. So like, remember, if the original function was, like 2x, we could tell that the inverse is going to be x over 2 because it's a reverse operation. So if you have more complicated functions, it's easier to use these guidelines. So the ones that are coming. So the key step is to exchange x and y. This is because the fact that inverse functions have ordered pairs with the coordinates reversed. In other words, the domain becomes the range and the range is the domain for the inverse. So let's see. So first of all, if we want to find an inverse function, we use the horizontal line test to see if it even has one. And then in the equation for f of x, we replace f of x with y. Then we change the x and y and we solve for my new y. And now we replace the new y with f inverse of x. Okay, and then we can double check that they're inverses of each other by taking the composition both ways and getting the identity back, or x back. So of course we need to do a super fun example. Where would we be with? Okay, so let's find the inverse function of f of x is equal to 5 minus x over 3x plus 2. And this is what the graph looks like. This is the 5 minus x over 3x plus 2. Okay, so has a little, its asymptotes are the x-axis and then this here. Right, so this is our graph, okay, and we're going to talk about how do I find the inverse function of this, knowing that this is my graph. Okay, so here's the steps. This graph does pass the horizontal line test, as you see in the previous picture. So we know that it's f to 1 and the function exists, the inverse exists. So first we write down the original function, okay, fine. Then we take this f of x and we replace it with y, okay, check. Then, this is the fun part, we take the y, the old y becomes x, and the old x becomes a y. And so now, we're trying to solve for y here, so let me multiply each side by 3y plus 2. So here on the left side, I get x times 3y plus 2 is equal to 5 minus y. So that'll cancel this one out. Then, of course, I'm going to distribute this, yeah? So if I distribute it, I get 3xy plus 2x is equal to 5 minus y. So what I need to do here is I need to add both sides by y. So on the left-hand side, I'm going to get 3xy plus y. And I need to subtract both sides by 2x. So on the left-hand side, I get 3xy plus y. And on the right-hand side, I get 5 minus 2x. Okay, now that I have that, let me factor out this y real quick. And then I get inside here a 3x plus 1 in parentheses is equal to 5 minus 2x. So now in order to solve for y, I divide both sides by 3x plus 1. And then now that I'm solved for my new y, I replace this y with f inverse, okay? And then I get 5 minus 2x, f inverse of x is equal to 5 minus 2x over 3x plus 1. And I can let you check this to see if it's correct, okay? So let's look at a couple homework problems. Okay, so number 13, show that f and g are inverse functions A algebraically and B graphically. So algebraically, so f is 2x and g is x over 2. So I kind of did a problem already like this. So f of g of x, so this would be my inner function, is going to be 2 times g of x. In other words, f of x over 2 is going to be 2 times x over 2. 2's cancel out and we get x. Great. Now g of f of x is going to be g of 2x. So what does g of x tell you? Hey, take something and then divide it by 2. So you took 2x and divide by 2, and you get x again, so there it is. And if I graph these two, you can see that they are symmetrical with respect to y equals x. All right, so then in this one, it says here, find the inverse function of f, graph them on the same axes, describe the relationship, and state the domain. Okay, so if my original is x to the 5th minus 2, 5th power, I would add 2 to both sides, right? So this would be my x and this would be my y. So add x, so you would get x plus 2. Then I would take the 5th root of both sides. So that's the 5th root of x plus 2 will equal my inverse function. Okay, then I can graph these using the graphing calculator on the same axes, and you will see these two. So this would be y1 and this would be y2, I guess, either way. And then you can see that they are reflected across the line y equal x. So that would be C, the relationship. And then the domain and range. So the domain of f is all reals and the range is all reals. So therefore the domain of the inverse is all reals and the range is all reals as well. Okie dokie, that's it for 1.9. That's your homework. Good luck, and I will see you on the next video.